go. Right, this is the P1 Energy Masterclass, or the Paper 1 Physics Masterclass, I should say, for the Paper 1 AQA Physics Paper. So we're going through today the key ideas so that we know what we need to remember for the exam tomorrow. So the first topic here is energy. And when you have a look at energy there, we've got this idea of energy stores. Okay, and so this first brainstorm is, what are the forms of energy that you need to know? So I'm going to move quite quickly through these slides here, but do feel free to pause them as you're going along. So you've got your different forms of energy. I'm going to go straight to what we actually need to know. Okay, so you need to know about your thermal energy, same as heat, anything hot. Your light energy, this is anything that gives off a light. So think about light bulbs, Bunsen flames, torches. If it gives off a light, we're talking about light energy. Sound energy, anything that makes a sound. Elastic or strain, sometimes we call it elastic potential. This is anything that has a stretch. Gravitational or gravitational potential energy is anything that is up at height. Okay, so this could be a book on a shelf, it could be an aeroplane, it could be a man standing on a cliff. Kinetic energy is to do with movement, so anything that is moving. And then your electrical energy, anything that uses electricity, as it got a plug, then we're talking about electrical energy here. Chemical energy is usually a store of energy. And so here we're talking about batteries, food in your stomach, because it's a store of chemical energy. Matchsticks, okay, the store of chemical energy that's released once you light it. And candles as well have a chemical energy. Nuclear energy, again, is anything related to nuclear fuels, right? So we're talking about something like the nuclear bomb. A lot of energy is released when you have a nuclear bomb going off. And in a nuclear power station, we can harness the power of nuclear materials in order to create energy, to transfer it to energy that is useful to us. Okay. And so in terms of in the exam, and again, this is a PowerPoint, so we've got ideas under here, which is really annoying, but this idea of conservation of energy. So remembering that energy cannot be created or destroyed is underneath here. It can only be changed from one form to another. Okay. And so there's an example here. A ball will gain gravitational potential energy when you lift it up above the ground, and when you drop the ball, it starts to move. So that is turned into kinetic energy. So the gravitational potential energy is turned into kinetic energy when it's dropped, and sound energy and thermal energy when it hits the ground. It makes a noise when it hits the ground. In the exam, we want to use the word wasted energy. The language we want to use is wasted energy is transferred to the surroundings as heat. Okay, so hopefully, again, this is easy marks for us in the exam. And so there's a couple of questions again, because of time here. Again, you can come back and pause this if you need to, but I'm just going to move through here so we can pick up the big ideas, because we want to look at the first couple of topics and it's a lot of stuff. Okay, so this is all about energy transfers. If you can remember, this is a good one here. Our input into the TV is this electrical energy. Okay, that's what's going in because you plug it in. The outputs here are light and sound, which are both useful forms of energy. And the heat that comes out the back of the TV is wasted. And we can look at this and we can talk about energy efficiency, which is how efficient is the appliance that we're looking at. So we could look at what we would do is we'd take what is useful, so the light and the sound energy. You will be given a numerical value in the exam. It may be a Sankey diagram, which I'll show you in a minute. So you take your useful energy, you divide it by the total input of electrical energy, and that gives you a number. It's a ratio of energy efficiency. You might be asked for percentage energy efficiency, in which case you multiply that number by 100. Okay, so energy efficiency in itself is actually a ratio. Okay, so again, there's lots of tasks here. This is talking about efficiency now. So when we're talking about efficiency, we want to have appliances or houses that are very efficient. When you buy a house, you get something like this, one of these kind of sheets. It tells you how efficient the house is. So what that means is how well, I suppose, does it use the energy, and how less energy is wasted in the house. Okay, and the kind of things you'd have on a house to make it more efficient is you'd have things like double glazing, you'd have things like loft insulation, you'd have things like cavity walls, and that means that when you're heating up the inside of that house, you can save money. So it's more economical because you're not losing or wasting any of that energy as heat. Okay. Environmentally, this is important because it means that if you're not wasting as much energy, if you're not losing as much from the windows and from the doors, you're using less fossil fuels. So therefore, we're adding less pollutants like carbon dioxide to the atmosphere. Okay, so there's a real kind of context around this. This is what I was just talking about earlier. Efficiency, if something is more efficient, that means that it gives you a lot of useful energy output, like the TV. Okay, and so to calculate the efficiency, again, you take your useful energy output, you divide it by the total energy you're putting in, and you multiply it by 100 to give you a percentage. This may, as I said, just be a ratio. Okay. And they've just put here small number divided by the large number. So this is like working out your marks in a test, for example, right? What you would get divided by the total marks that you could be getting. Now, as well as the efficiency with energy, you could be asked about the efficiency using power. Same principle. The useful power output divided by the total power input multiplied by 100. And before you multiply it by 100, it says here you should always end up with a decimal. Okay, so just be mindful of that. Now, I'm going to scroll through some questions on here. Again, the answers are on here as well. Please feel free to come back and do some of these energy efficiency calculations. These are easy marks in the exam, fingers crossed, to pick up. Got a 1 marker, and there's 2 marks here. Always write down the numbers that you're using with your substitutions, and please put the units in as well if you know what the units are. Energy is measured in joules, really, really important. Okay, another couple of exam questions about energy transfers. Again, okay, this one is worth looking at. This is called a Sankey diagram, and you may get this in the exam. And so here, the widths of the arrows show exactly how much energy is transferred in each particular way. And so what you've got is you've got this section here, you've got 20 squares here. It shows you the input, okay? And it's always done in proportion. So here, they've said there's 100 joules of energy in crude oil. So this is your input on this side, okay? Then it shows that you've got these arrows coming out. These are your different outputs. Usually the biggest one is going to be the wasted one. Okay, and so here they've said complete the diagram by adding the correct energy value alongside each row. So they've told you that 80 joules of energy is in the petrol. Okay, and so here, what have they put? 80 joules of energy is in the petrol. So you've got in total here, 20 joules of energy is used to refine the oil and transport the petrol to the filling station. So that's here. And look here, they've got 4 squares. Okay. And over here, you've got this wasted energy, which is your 60 joules of energy wasted by the car engine. And at the top here, you've got your 20 joules of energy, which is used to make the car move. So to work out what you've got, first of all, you've got 100 joules coming in. So everything coming out needs to equal to 100. So 60, 70, 80, 90, 100. Right? So input and output always has to be equal. So look at those numbers. And here they've just worked out if 20 squares is 100 joules, then 1 square must be 5 joules. So you've done a quick conversion. You might be asked to draw one of these. More than likely, you're going to be asked to put the numbers in, particularly at foundations here. Okay, right. Moving up, and again, the other part of the question, again, do feel free to pause and have a look at this. The answers are all on there for you. Right, higher tier for you, Emma, increasing the efficiency of a device. So this is how can we make something more useful, okay? So what we need to do, it says the total input energy or input power will usually be constant. So when you're suggesting an improvement, we must look at increasing the amount of useful energy. So that top number on the efficiency, we want it to go up. How do we do that in real life? We're going to reduce the wasted energy by, increasing the useful energy or reducing the wasted or making the wasted go down, which means useful goes up. Hopefully that makes sense. So we can lower the electrical resistance in a device okay? Which means if you've got less resistance, it means you've got less heat production in things like, by using things like LED bulbs instead of filament lamps. Filament lamps, like the normal bulbs that you get, they tend to get quite hot. The LED ones don't give off as much heat. Okay, so you can like touch them and change the bulb without burning yourself. And that will obviously reduce your wasted energy because you've got less coming out as heat. Reducing friction. So if we have a smaller surface area of a contact surface, so the more surface areas are rubbing against each other, the higher the friction, and therefore you've got thermal energy loss there. If we can reduce that contact area, that means that our friction also goes down. And overall, by reducing heat loss in any system would help you make a device more efficient. Okay, right, doing work. So by putting energy into a system, okay, so by pushing something, by compressing a spring or stretching it, or by lifting something up, you are doing work. Okay, and this is where I want to see whether the formula's down the bottom or not. So you've seen that you've got the full formula sheet, but the work done is equal to the kinetic energy, the gravitational potential energy, or the elastic potential energy, depending on the work that's being done. Okay, so if something is moving, calculate the work done. If you've got something that's being lifted, gravitational potential. If something's being stretched or squashed, it's the elastic potential energy. So have a look here. Right, and this is where I'm going to start scrambling in the book here to look for the work done here. Bear with me a second to make sure that I get the right formula for you. I'm pretty sure this is also on your equation sheet. Okay, so you've got here, which one are we using? Oh, this is really annoying. I'm not going to be able to find this quick enough. Bear with me. Right, hang on. Let's just come back to here. Let's just find it in here. It'll be a bit easier. Number of joules here. FS. Right. Give me a second. Why can't I find this quick enough? My brain is clearly slowing down. I'm just going to quickly actually look it up in the back. 11, 14, 32, 53. Bear with me. Okay. Time. Let's do the gravitational potential. Right. I don't know off the top of my head. I don't know what formula has been used here, but what I should have done is added it to the actual thing here. Okay. Emma, do you remember what this formula is? Put me out my misery.
No, I don't.
Oh,
Sorry.
right. Hang on. Let's see if we can find it on this sheet. That will probably be a sensible thing to do. Here we go. Look here. These are the two that I found. This one, work done over time. Power work done over time. But my brain's not quite kicking into gear yet. That's okay. Oh, here we go.
There's
It's
one
this one.
here. Yeah.
There it is. Right. So what we've got is work done is force times distance here. And again, annoyingly, I'm really sorry, it's not on that PDF there, so don't be confused by it. It is on your formula sheet. This is W equals F times S. And this kind of now makes sense if we go to here. So work done equals obviously force measured in newtons over the distance that the object is pushed, which is in meters. And this is why when we get to our question, okay, when they've calculated the work done, you've got the force here, which is 220 newtons, which is from the question here, to push a wheelbarrow up the plank, and it's being moved by a distance, which is your S, of 2.6 meters. That's how far the guys pushed it. Multiply those two together, that will give you your work done in joules. We got there in the end. Okay, and again, same kind of thing. Look at the question. You've got your formula sheet, fingers crossed, like we'll have that there so we can use it. Same principle. Your force is in this question is 60 newtons. Again, you can pause it and have a look at the video if you need to. Your distance is 28 meters. Where's that from? He's pushing the crate 28 meters here. So you multiply those two values for work done. Okay, So kinetic energy, do you know what? I'm just going to go back to the fact that the actual sheet's probably quicker than me looking in the book. So your kinetic energy is right at the top here, as we looked a minute ago. So here's where you've got your half times mass times speed squared. Okay, and this in symbols, E and a little k is half mv squared. So here, again, your units of energy is always measured in joules, your mass in kilograms, and your speed is meters per second, and you've got to square that value to put it in. Quick exam question here. So again, you've got your half, your mass in the question is 1600 kilograms. Let's see where it is. Here it is. Okay, your velocity is 20 meters per second. Here it is in the question, and we're going to square that 20 before we put it in. For some reason, there's no working shown here. Obviously, in your answer, there's 2 marks here. Show the formula that you're using, even if it's from the formula sheet, and show your substitution with your answer, your final units. The units are given here for you as well. You should know kinetic energy. Is it measured in joules, this type of energy? Okay, right. Let's head through again. Another question. Do have a look and have a pause of the video. There's a couple more here. Okay. So,
Just
yep.
just quickly, this might sound really stupid, but in equations, is mass always in kilograms?
Good question. Generally speaking, yes.
Okay,
Yes. Okay.
thank you.
So just stick to the kilogram. That's all right. It's not a stupid question. They're the best ones. I like the best ones. So this idea of mass and weight. Okay. And so actually the slide probably explains it a little bit better. Yeah. So mass. I want you to imagine not this box, but say it's me or you stood on the earth. Okay. And then me or you going to the moon. Okay. Now, what's going to happen is our mass is still going to be 10 kilograms stood on the earth, and you're still going to be 10 kilograms if you're on the moon. However, you will have a different weight because the gravitational pull on the earth and the gravitational pull on the moon is different. And we can see here that, again, it makes it a bit more complicated with the scales, but your weight on the earth is 98 newtons. Weight is a force measured newtons. Your weight on the moon, however, would only be 16 newtons. Moon has a smaller mass, so you have less of a pull towards the center of the moon. Okay, less gravitational force. And here's where we're talking about gravitational field strength. So mass times weight. And now this formula, again, this is on your sheet as well. So this is a formula for weight in newtons. And so if I come to here, I'm going to highlight what I've got. Is it on here? Here is it. Oh, that's annoying. Okay, so the weight, here we are, it is here. Weight is mass times gravitational field strength, and this is W equals mg. And here the weight, remember, it's in newtons, your mass is in kilograms, and the gravitational field strength is going to be the pull of gravity depending on the planet that you are on. On Earth, the number that you need to know is they tend to use 10 newtons per kilogram. Sometimes this is 9.8. Okay, I think you would get the mark either way in the exam, but again, you're just multiplying those two values together to give you the weight in newtons. Okay, another exam question. If you want to pause it, you can do. Let's continue moving through because otherwise we're never going to get to the end of this. Okay. So when an object is lifted above the ground, there's a gain in potential energy. This is the change in gravitational potential energy. Okay, lifting something up, it is gaining or having a change in gravitational potential energy. The work done to put it there, okay, so the work that you did, effort, if you like, that you put in to put it up high is equal to the gravitational potential energy. Now, again, another formula. This is annoying having to keep flip back. The gravitational potential energy formula, again, is on your formula sheet. Where are you, formula sheet? Let's go to the top. Is here is your mass times your gravitational field strength times the height. This is your capital E energy, pictured in joules again, your little p for potential, and then mgh, mass, gravitational field strength, and height. So your mass measured in kilograms, your gravitational field strength in newtons per kilogram, and your height is in meters. I'm going to go back later and actually draw these in. This is really bugging me. Right, another question. I'm literally now just going to show you the question. If you want to come back, and again, it's just a case of plugging in. I'm quite conscious of how much we've got to cover this evening. Okay. Now, again, this is annoying because you've got a calculation question, you've got some values missing here. Okay, so just be mindful of that. Don't stress out about it. Right. Now, this idea of when you stretch things and you squash things, we're talking about elastic energy or elastic potential energy. If you stretch something or squash something, we can measure in it the work done as the elastic potential energy is equal. So this is as long as the only way this applies is if the limit of proportionality is not exceeded. And what we mean by that is when you have a spring or an elastic band, when you stretch it, the limit of proportionality is when you've overstretched it and it won't go back to its original shape, right? You've messed up the spring. And the number of times this has happened when we've done the Hooke's Law experiment in school, I can't tell you. Okay, we've ruined springs, really expensive. And so elastic potential energy, again, this is given on your full formula sheet, and I'm going to find it for you again to save me faffing about. It's just up here, is half times the spring constant times the extension squared. So the extension squared is how long, how much the spring or the elastic band has been stretched by. This is the energy of E, elastic potential energy, capital E, little e, equals half KE squared. Now, K is your spring constant. Now, usually in the spring constant, what the spring constant means is how much work do you need to stretch or compress an object? The bigger the number, the more work that is needed. Okay. And usually these are given to you in the question. All right. So the way the question will be worded is you've got a height here. Okay. You've got a spring with a spring constant of, and they tell you in newtons per meter, and then you're going to calculate the energy stored. So this is an elastic potential energy calculation. All right, got a bungee cord situation, a stretch or a squash. Again, you've got another higher tier exam question, and this is now using a rearrangement, look, because it's a higher tier, calculating the spring constant. So rather than calculating the elastic potential energy, you're actually in this case now given the spring constant to calculate. So rearrangement, it is a higher tier skill. Okay, power, power, power. This is the rate of energy transfer. Okay, the more powerful an appliance, the more energy is transferred over a period of time. And now there's two different formulae for power. In this one, again, I'll show you on the equation sheet while we're recording here. You've got the energy transferred over time, so P equals E over T, PET. You've also got power is work done over a certain period of time. Okay, so just be mindful there's two of them, and depending on the units, on the values that you're given in the question, just make sure that you're using the correct formula here. Okay, now the energy transferred, obviously, if you're given joules over time in seconds, then you're using this top one. If you're given, also work done is joules over time in seconds, that's annoying. Okay, so just be mindful, I suppose, which either one that you use, you'll still be using joules as unit on top and time across the bottom. So that is your power equations. And again, an example question here where you've got the number of joules of work going from the bottom of the stairs to the top of the stairs. It took them 2.8 seconds to run up the stairs. So E is 2240 joules divided by your 2.8 seconds. Again, show you're working here and then your final value plus your units. Right. Again, another exam question. Look for those units. You may need to be doing some conversions. Be aware, particularly higher tier. There's a couple more. Right, converting, here's an exam question with a conversion. So you've got 2 million, I want to say watts, okay, is the same as 2000 kilowatts. So just be confident with those conversions. You're dividing by 1,000, okay, to go from watts to kilowatts. Just be mindful. Right, I think we did mention this earlier on. In your house, and I think this is almost at the end of the first section here, so we are going to have to speed up a little bit. There are different ways of reducing energy loss or heat loss. And here you've got, you can have loft insulation. We did talk about this earlier. Double glazing and using curtains, thick curtains will again stop heat loss, reducing energy loss. The gaps in the doors are draft excluders and those things that come across the where you post the letters through letterboxes. They are also ways of reducing heat loss. in houses. And you've got cavity walls, which we've mentioned, which are tiny little walls like an aero bar or a crunchy bar, little holes in the walls when the houses are built. And also putting carpet on the floor, you'd obviously have less heat being lost through the floor as well. That's quite a nice one. Right, specific heat capacity. Again, you're given this in an exam, and you do have a required practical to do with this as well. So you'd use this formula here, okay, with specific heat capacity in it. And this is the change in thermal energy, thermal meaning heat, equals your mass in kilograms multiplied by the specific heat capacity multiplied by the temperature change. So the little triangle there means a change in something. And in this case, the change, and I think this is the letter theta, the change in temperature, your mass and the specific heat capacity is C. This gives you the change in thermal energy, so the triangle for the energy. And again, your units are here. Again, this should have a symbol in it. The symbols haven't obviously come up on this little PDF. Right, metals and conduction. In metals, the way that the particles are arranged, obviously metals are solids, okay? You can see we've got a regular arrangement of these grey particles in a metal. Now, what happens is with metals, they have outer electrons that don't hang around any particular atom. They are free to move. Okay, so when we heat up the metal, what happens is the free electrons take in that the thermal energy is transferred to the free electrons. They gain kinetic energy. They start to move. Now, these particles, sorry, the electrons can then move around the metal, which means they can collide with other metal ions. And so the heat energy is transferred through the metal. This is why spoons get hot when you have a pan of beans on the hob and you leave a metal spoon in there. That's why when you come and pick it up, it's going to be hot. Okay, so you've got, we call these delocalized electrons. Okay, that move around, that makes metals good conductors. Yeah. Okay, so that's your heat transfer question there. Okay, again, pause it if you want to have a look. The answers are all in here for you. That should help you out. Just moving through. Okay, this is a specific heat capacity question. I think quite likely to get a specific heat capacity question. All right, it's a couple. Wow. Right, this is your required practical, and a reminder, your control variables with the specific heat capacity required practical. So what you did was you changed the substance that you put as you changed the metal block. I think that's how we did it at school anyway. So you've got a metal block here that's covered with lagging. You've got a heater that's on this little kind of pulse, like a probe heater. That's connected to a power pack in order for the heater to work. And then you've got a thermometer here that is measuring the change in temperature of the block. So you change the metal of the block. We are going to measure the specific heat capacity of the different materials. Okay, so I remember when I did this in school, we did a copper, we did aluminium, and we did another metal block, probably, I don't know, I want to say lead. And we looked at the temperature change. Now we are measuring the current using an ammeter. We are measuring the voltage using a voltmeter here. And we're going to control the mass of the block, keep it the same, the starting temperature of the block, and the time we're going to heat the block for. So you'd have a timer here as well. Now, the reasons that you might not get great results here is we could be losing energy to the surroundings, okay? And this would make our specific heat capacity lower than we expect it to be. Right, again, you've got steps here in the required practical. By all means, do have a pause and then have a look through the different steps so you know what you're doing. Right, so here you've got, and again, right, you've got energy resources. Now, alongside here, these are different resources that we have for energy, right? And usually we're looking at producing electricity with them. So I can't move these blocks. I'm sorry, I've transferred it to a PDF. But here you've got biofuel, wave, wind, hydroelectric, tidal, solar, and geothermal. These are all renewable forms of energy resources. You should have an idea of what each of these are, okay? And because they're renewable, they are easily replaced and they will not run out in theory. However, when you're talking about nuclear and fossil fuels, these are non-renewable fuels. Okay, particularly fossil fuels because of the way that coal, oil, and gas, the fossil fuels, were formed. They were formed millions of years ago under specific conditions of dead animals and plants have fallen down. They've started to decompose. You've got soil and sediment falling on top of them. You've got pressure, 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 and heat, heat, heat from underneath. And over millions of years, that's what's formed crude oil, coal, and gas. Okay, natural gas. So that's your fuel, fossil fuels. Nuclear fuels are also technically non-renewable as well. And again, there's lots of advantages and disadvantages of nuclear fuels. Advantages, actually, the energy that you get from nuclear fuels is actually really, really high. The disadvantages, when you when you create or build a nuclear power plant, it obviously takes up a lot of space on the landscape, if you like. They're very unsightly. But also one of the big disadvantages is the potential of having some kind of nuclear disaster. It is quite high. Okay, so think about not Hiroshima, Chernobyl, and there's one that's mentioned in the revision guide. I think it's called Fukushima as well. Again, nuclear power plant's gone wrong. Okay, this means that the background radiation, if you have a nuclear explosion, the background radiation in the environment remains really high. This causes problems because you have radiation in people. Okay, and background radiation in buildings and plants and animals are affected. People that are pregnant end up with giving birth to deformed babies, increased chances of cancer and other illnesses like that. Okay, it says here carbon capture can be expensive, but they are used to capture and store carbon dioxide. So again, just have that in your mind. You've heard it now, just in case it comes up. Right. Let's start moving on. So triple only is the insulation practical. Emma, you're not triple only, so we're not going to spend any time on it at all. But you've probably done this as a Key Stage 3 practical anyway. Your 3 jars, you cover them with 3 different coverings and look at temperature change over time. Okay. Again, we've got steps over here and set results. We're not going to spend so much time on it because we're going to get you sorted. Right. Thermal absorption, here's a bit of language here. In terms of thermal absorption, so heat taken in. If something absorbs heat, it takes it in. If something emits heat, it gives it out. So this is just a little technical thing here. Right. Thermal absorption and emission. Black is going to be the best thermal absorber of radiation. This is why on a really hot day, you don't want to be wearing a black t-shirt. You're going to be really, really hot. It is also the best emitter or giver outer of radiation as well. Okay, so cooker hobs are usually dark colors. Car radiators are often black so that they emit as much energy as possible to keep the car radiator cool to stop it overheating. Okay, so thermal emission. Silver surfaces are bad emitters of thermal radiation. Okay, so we can use them when someone's here, someone's not very well by the looks of things. They will help to keep that heat in to maintain someone's body temperature after a marathon or race or something like that. They give you this foil blanket. Now, so electricity, let's go. Now, the first thing with electricity is that you have your set of circuit symbols. And so you need to, in your revision guide, make sure you know what the circuit symbols are. Again, I'm really sorry, the images haven't shown up on here. It's pretty useless at the moment. Now, what you might be asked to do is to draw a circuit diagram. Okay, again, it will be 1 or 2 marks at the very most. So you'll be given an image of some sort and asked to draw it out. And when you're drawing, please use a ruler. Take a ruler to the exam. A reminder, when you're putting an ammeter into a circuit, you are putting the ammeter in series, which means next to the other components. And when you're putting a voltmeter into a circuit, it goes in parallel, so across a component like this, sticking out across it. A series circuit, just a reminder, a series circuit is when you have components placed next to each other, like a TV series, one after the other, right? Like they're all holding hands in a circle. And then a parallel circuit is where you have like a go-kart track. Think about the current flowing around parallel circuit. You have more than one path that you can take. If you're the current going around this circuit, you can go round to this first bulb, but you can also go round to the second bulb. So if there's a problem with the first bulb and that's fused and there's nowhere for the current to flow, you can always go down the other path instead and look and go for the second bulb. Okay, so you've got an alternative path to follow. Right, again, another exam question. Use a ruler to draw circuit diagrams, please, please, please. Right, definitions. Current, the flow of charge per second in a circuit. We measure current in amps. We use an ammeter, and this is represented by the letter I in formulas. Potential difference is the energy per unit charge. This is measured in volts. We use a voltmeter to measure potential difference, and it's represented by the letter V. Resistance is a measure of how difficult it is for the current to flow. So think about current flowing and you're pushing against it. Okay, the higher the resistance, the higher the greater the difficulty for the current to flow. This is measured in ohms, which is the funny symbol here, represented by R in a formula, and can be worked out by potential difference divided by current. V divided by I gives you the resistance. Okay. And again, annoyingly, we've got the equations. Let's see if that's on our sheet. I don't think the current one is. Why do I think it's not? Let's have a little check. Am I missing it? No, it's not. Here we go. It's this one. Potential difference equals current multiplied by resistance. In other words, V equals IR. Okay, this is what we call Ohm's law. All right, so you've got that on your formula sheet for this year, so you're all good. Okay, so again, another exam question. How are we doing, Emma? Are you okay?
Yeah, I'm good.
Yeah, too quick, too slow, all right?
It's pretty good.
Good. Okay, right. I'm going to keep going through. Are you okay if we go over a little? I'm going to try and go quick. I promise I will.
Yeah, that's okay.
Okay, let me know when you're done. Like if you have to go, you have to go. That's okay. I'll just carry on through and finish it off and pop it over to you. But
Okay, thank you.
just if you're knackered, I appreciate you got your exam tomorrow. If you're knackered, just as I said, just give me a shout and then we'll call it.
Okay.
Okay, right. Charge flow. So work is done when charge flows in a circuit. So again, we're going to go back to the formula sheet here. Here we are. Charge flow equals current multiplied by time. So this is your Q equals IT. Q, IT. Here we've got what we got. Let's go back because I've got it muddled up in my head. Charge flow equals current times time. Okay, no, that's fine. I'm just checking what we've got here. So that is the amount of energy transferred by electrical work can be calculated using this equation. So this is energy transferred by electrical work. Let's see if we can find the correct formula here. Here we go. I think energy transferred. Let's have a look. What am I missing? Here we go. Energy transferred here is charge flow times by potential difference. So this is energy transferred, which is measured in joules. Your charge flow is your Q, okay? And then your potential difference is V, which is measured in volts. I'm just going to go back and check the units for charge flow. Charge flow is C, and I'm going to also double check that because my brain is just about to lose it. Charge. Oh, why can I not see it? Okay, I can't easily put my hands on it. Roughly what it is. Here we go. Yes, the charge flow is measured in coulombs, which is C. I just want to double check, make sure I've got that right for you. Okay, so this is your Q equals I. No, it's not. It was the other one. Oh gosh, listen to me getting muddled up. This was your charge flow times potential difference. E equals QV. Gosh, we'll get there in the end. Q and V, which makes sense. E is energy. Right. So we've got this question here again, and I'm hoping the second, again, I don't have the answers straight up here, but we've got this. And so we've got the mains electricity supply at 230 volts. The different heater transfers energy, 4,200 joules of energy. Calculate the charge flow. So we've got the volts, we've got the joules, we've got the charge flow. So the formula we're going to use is this one, the joules, the volts, and the charge flow. So we'd rearrange E equals QV for this one, and then making sure, go back to it, we put our things in the right place. So we've got our 230 is V, we've got our 4,200, which is joules, and then you work out what your C is there. Okay, and that should give you a charge flow of 18.3. Again, show you're working in an exam. There's 3 marks for this formula, even if on the equation sheet, write it down. substitution, and your units in as well. They've given it to you here. You may need to figure out the units. Okay, nice and clear. Right, voltage, here we go. And again, going back to the sheet, got V, A, and in ohms, voltage, voltage, voltage. Let's find you. No, I've got it here. It's a potential difference. So this is the formula that links potential difference, current, and resistance. We did it earlier on. So this one here would be potential difference in volts equals current in amps multiplied by resistance in ohms. Okay, so potential difference is current multiplied by resistance. Again, making sure the units are correct. If we come along here, again, hopefully I'm hoping, look, they've given it to you here. It's an easy one for you to pick up marks in the exam. Typical question is here, and how many marks? It doesn't say how many marks here. I would imagine 1 or 2 marks here. Okay, again, another exam question, pause it if you need to. This is a 2 marker and a third. Okay, so rules of circuits. So again, and I think we did this together very recently, actually, Emma, it's ringing a bell. In a series circuit, the current stays the same anywhere you are in the circuit. However, the potential difference, V, is shared between the components. So the total resistance in a series circuit, you're adding up the resistances of each of the components. If you've got a parallel circuit, this is where you've got your go-kart track, where your current can split. The potential difference will stay the same anywhere in the circuit. However, the total resistance is less than the lowest, the lowest individual resistor. Okay, that sentence doesn't make sense to me. Current and series in parallel, again, it gives you this beautiful example here. It takes you through what happens. We said in a series circuit, look, the current stays the same anywhere. This is quite a good diagram. Whereas if you've got the current in a parallel circuit, look, you're splitting it 3 ways. So we're starting off with 9 amps. Okay, current is measured in amps, is I, right? This, you've got 3 here, 3 here, and 3 here. You've got a splitting effect, right? And then in series, okay, got Ohm's law. This is V equals IR. Okay, V equals I times R. So which factors will affect the resistance of a wire? Okay, and there is a required practical on this. How long, the length of the wire will affect the resistance. The thickness of the wire will affect the resistance. How many components there are in the circuit will affect the resistance, and how hot the wire is will also affect the resistance. You may remember doing the length of wire and resistance. This is where you had your wire, you've got crocodile clip one end and crocodile clip the other end. And what you're doing is you're changing the length of the wire. If you have a look at this circuit here, okay, you've got crocodile clip here on the end, and you change the length of the wire. You measure the volts using a voltmeter, you measure the current using an ammeter, and then you use your resistance formula, which is resistance equals potential difference over current, to work out the resistance at different lengths of wire. Okay, and so what you're going to find in the results here, which is quite helpful to have, is as your length of wire increases, the resistance increases. It's a proportional relationship. Now, the crocodile clip might put into your experiment, you may have what we call like a systematic error, which means you might not get the crocodile clip right at 0, which means a systematic error means if you put it on like 0.1 centimeters on the ruler, all the way through your experiment, you're out by 0.1. That's called a systematic error, an error that is constant throughout the whole experiment. We've got a low potential difference as the short length of wire. Hang on. With a low potential difference as a short length of wire, the current will increase dramatically. Okay, so just again, there's your results that require practical. Now another one with resistors here. Okay, so you've got 2 different circuits here, and you've got resistors put in different places. And I think my assumption is that you're measuring resistance across these circuits and having a look at what happens when they're placed next to each other and when they're placed in parallel to each other. Right, again, some resistance questions. So the resistance total in a series circuit is the sum of all resistors. So this, again, hopefully straightforward calculations where you're just adding up the resistance to give you, to here in this example, 9 ohms and 6 ohms gives you 15 ohms of total resistance. You just added them together. Right, IV graphs. You're going to need to be able to name the component for each of these graphs and know the shapes of the graphs. So this is an ohmic or a fixed resistor. You've got this directly proportional relationship as long as the temperature is constant. Okay, now the axes on all the graphs are potential difference going across and current going up. With a filament lamp, you get more of an S shape, and with the diode here, you've got, because with the diode, you can only have the current flowing in one direction, so you have this effect where you've got this positive relationship here, and then you've got a flat line. It doesn't go into this bottom negative region at all, right? In your revision guide, you've got really, really nice descriptions of each of these and the reasons why these graphs look like this, okay? Again, conscious of times moving through. So thermistors and light-dependent resistors. So your symbols here, thermistor and light-dependent resistor. The way that I remember it is these two arrows represent the light. So is your resistor with the two arrows of light hitting it, whereas your thermistor is here. So with a thermistor, the resistance will depend on temperature. As your temperature increases, the resistance goes down. Look at the shape of the graph, right? Then, for example, in central heating, if it's getting really, really hot, well, actually we want less resistance. Okay, and then same thing in the fridge as the other example. Light dependent resistors. As the light intensity increases, look at the bottom axis here, the resistance also goes down. Okay, so these are used to control shutters in digital cameras. Okay, so if you've got low light, so if you looked at the aurora borealis the other night, what happens is that you've got a slow, I don't know what you call it, a slow shutter speed in order to capture the different colors on your phone. Right, AC is called alternating current, DC is direct current. So the potential difference of mains electricity changes direction. Okay, so that is what usually where you have AC. Mains electricity, so from a plug is AC in and is at 50 hertz. It's changing direction 50 times a second. Think about sound waves. Direct current is the potential difference across cells and batteries is in the same direction. Potential difference does not change polarity. You don't get positive or negative. If you have a battery or solar cell, they are in direct current, okay, or using a direct current. In a graph, you might get something like this. Because the alternating current has a positive or negative voltage, you get like a flip-floppy graph here. And with the DC source, look, you cannot get in the negative region, so you have a straight line graph. So DC direct current, straight line graph, whereas alternating, you're going positive, negative across. Okay. Mains electricity is an AC supply. In the UK, the frequency is 50 hertz, know that number. The voltage is 230 volts. This is the electricity coming to your house. When you have a plug, you need to know how to wire it. This is a life skill. So when you, hopefully you've done this in class. Inside the plug, you've got a fuse here that looks like this. You've got two metal ends of a fuse. In a glass tube, you have a low melting point wire. So if you have too much of a current pumping through the plug, that wire will actually melt and it will break the circuit and stop you getting electrocuted, hopefully. This is when a fuse blows. The earth wire is a green and yellow stripy one. Your neutral wire is your blue one, and you've got your outer insulation of the wire to stop you getting electrocuted. Your brown wire is the live one. The live wire carries the alternating potential difference. The neutral completes the circuit, and the earth wire, green and yellow stripes, is the safety one to stop the appliance becoming live. Okay, so just know those colors. Right, so as I said a minute ago, the fuse contains a very thin wire here. And so if the current is too high, the wire will heat up, and as it heats up, it will melt. It will break the circuit. This is a safety feature of the circuit. If you've got a 3 amp device, you would use a 5 amp fuse. If you've got a 10 amp device, you'd use a 13 amp fuse. Again, just common bits that come up in the exam. And again, I'd advise you just to pause this and make sure you know why these answers to these exam questions are as they are. Right, power. So let's get to the right page here. So you've got, what have we got? Voltage, V and I. So let's have a look at electrical power. We had a couple for power on here. So this is our equation sheet here. First one is power equals V, potential difference times current, potential difference measured in volts, times by current measured in amps. Okay, I think I'm getting my second wind. I can feel it coming on. And then, so using this, current's measured, power's measured watts, by the way. So you've got your formula here. Again, substitution. If you want to pause the video and have a look, where do they get the values from? And make sure you can get that power value. Another exam question here. Keep running through. Goodness me. Right. National grid. This is how we have a system of cables and transformers. And this is how we connect a power station where we, I want to say create, that's not the right word, transfer electricity. The electricity goes through a step-up transformer, okay? And what this does is it increases the potential difference from the power station to the transmission cables, and it lowers the current, right? So in other words, we've got high voltage and low current coming through the step-up transformer all the way to your power, these pylons, passes all the way through. And when that electricity reaches the house, was about to go into your house as a consumer, the step down transformer is used. And what that does is it lowers the potential difference and increases the current. So in this case, you've got a lower potential difference, lower voltage, and a high current before it gets into the house. Okay. Okay, step-up transformers, why are they used? So when that power comes out of the power station and into the actual grid. The step-up transformers are used to reduce the energy losses due to heating in the transmission cables, right? We want to reduce the energy loss due to heat. To calculate power loss, now I'm going to have a quick look, see if I can find this. Power loss. Don't think it's in here. Okay, again, there's something missing here. Don't panic too much about it, but it is what it is. Emma, we've got static. We're not going to look at static charges, but again, this is triple only, so we're going to whiz through. Not even going to mention anything. And I think electric fields is the next bit. It's another question. Okay, you're glad you don't have to do this. Right, P3, particles and matter. You need to know how the particles are arranged in a solid, the end here, in a liquid and in a gas. In a solid and liquid, please, please, please remember that you have particles that are touching each other. They touch each other in solids and liquids. This is why you can't squash a solid and you can't squash a liquid. In a gas, particles move freely. And so this whole idea, again, you can pause the slide. This is very much sort of key stage 3 ideas of definite shape, definite volume for a solid, touching particles, vibrating on the spot. So we say particles vibrate about a fixed point. There's strong, attractive intermolecular forces between the particles. That means the particles have lots of forces between them. With a liquid, sorry, we've got low kinetic energy here. We can't squash them, rows and columns. Liquid, no definite shape. Liquids flow. They take the shape of the bottom of the container. You can fill a glass of water, right? Or you can spill water on the table. They have a definite volume. Particles are loosely arranged and they slide over each other. Okay, here it says 50% touching. I'm not sure how, I don't think that's correct at all. We have medium intermolecular forces between the particles. So there's some forces, but definitely not as much intermolecular forces as the solid. They have a medium kinetic energy. Okay, so again, some movement with the particles. We cannot compress them. With gases, they have no definite shape. They fill the shape of the container that they're in. Think about kind of deodorant or gas in a room. They have no definite volume. The particles like to spread out as far as they can. Very low density, right? Density, heaviness, particles are light. Particles bounce around and collide with each other at high speeds. Boing, 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 right? It's what creates pressure. Very low intermolecular forces between the gas particles. It's so far apart. We've got very high kinetic energy, a lot of movement between the particles. We can compress a gas because they have spaces between them, and the volume increases with heat. Okay, and that is because as we give the system heat, the particles gain the thermal energy and they start to move more and bounce off each other. And so as they're bouncing off each other, they take up a greater volume. Okay, right. Changing states again, year 7 ideas. How do we change from a solid to a liquid to a gas? We've got these arrows here, right? So if we think about ice as a specific easy example, melting ice, turning it to liquid, vaporizing the ice, turning it to a gas. If we get our gas, if you come out the shower and there's steam, it condenses to a liquid. And then if we take that steam, collect it up, put it in the freezer, we can make ice blocks, right? We freeze it. Sublimation is when something goes directly from a solid to a gas, okay? And deposition, again, something goes from a gas to a solid, right? So density, how much matter is there in a given volume, right? In my head, I think of it as the heaviness of something. So with density, again, should be on your formula sheet. Let's see. Oh, here we go, just missed it. Density equals mass divided by volume. Mass in kilograms divided by volume in meters cubed. Okay, so density equals mass divided by volume. The mass of regular and irregular objects. So, and I know, Emma, we did this recently. This is where we use our Eureka can, which is the same as a displacement can. You fill it with water up to the point. You then put your irregularly shaped object in it. So it might be a rock, it might be a, I don't know, whatever it might be. The question a few years ago on chess pieces. And whatever is the volume of the object that you've put in, the water will be displaced out the Eureka can, and you can actually collect that water up. It's like water coming over the edge of a bath. Then that then gives you the volume of the object. You can then look at the mass by putting it onto the scales, and then you can do your calculation for density. Okay, so that is that. Again, a couple more questions. Right, internal energy. All objects and systems contain internal energy. And this is the sum of all the kinetic energy of the particles and potential energy of the particles. So internal energy is kinetic energy plus potential energy. When we heat up an object or system, the particles start to move around, the internal energy increases. That's because particles move around more, it's more kinetic energy. Right. Specific latent heat of, let's get this right, get the right page, specific latent heat of what we got, vaporization and specific latent heat of fusion are the two. I'm hoping I've got those two correct. Latent heat of fusion and latent heat of vaporization. Yeah. Okay. So the first of all, so the amount of what we got, fusion is if you go from a solid to a liquid and liquid to solid. Vaporization is liquid to gas and gas to liquid. The formula is the same. And so this graph you should be familiar with changing states from solid to liquid to gas, okay? And then the phase change, these flat areas are when you've got, like the diagram we looked at 2 diagrams ago, the melting phase and the vaporization phase. So the amount of energy required to change the state of 1 kilogram of a substance from solid to liquid with no change in temperature. Okay, so where we've got the red lines on this diagram, the temperature is increasing. The blue lines is where the temperature is constant because you're changing state. Okay, so that's the specific latent heat of vaporization in this case, getting hotter. In this case here, specific latent heat of fusion. Let's have a look at this. This is given in your exam. Let's find it, specific latent heat. See how quickly I can find it. Okay, I'm not going to be able to find it. Potential different thermal energy. Here we go. It's this one here. So the thermal energy change for a change of state, okay, and this should be measured in joules. I'll check on the other sheet in a minute, equals mass times your specific latent heat. E equals ml. Okay, so the thermal energy for a change of state is mass times specific latent heat. So if we come back to here, yep, there's your energy in joules, your mass, which is in kilograms, and your specific latent heat is joules per kilogram. Just be mindful of those units there. Again, another exam question, and we're moving on to pressure. So temperature of the gas is related to the average kinetic energy of the molecules. The higher the temperature, the greater the kinetic energy, particles are going to move more, the faster the average speed of the molecules, right? So when molecules collide with the wall of their container, they exert a force on the wall. right? The total force exerted by all of the molecules inside the container on a unit area of the walls is the gas pressure. What they're saying is the number of times these particles bump with the sides of the wall is equivalent to the pressure. Okay, you've got 10 tons of particles in there, so you filled it with gas particles, and they're bumping with each other and bumping with the sides of the container. You have a high pressure situation. So the pressure law. By changing the temperature of a gas at constant volume changes the pressure exerted by the gas. Increasing the temperature increases pressure. Decreasing temperature decreases the pressure. This is the pressure law. Okay, it's particle motion in gases. We're nearly there. We're nearly there. Right. So changing the temperature of a gas held at a constant volume changes the pressure exerted by the gas. It's just the previous slide repeated by the looks of things. Triple science only is Boyle's law, so I'm going to leave that out for the minute for you, Emma. And now we're on to topic 4, radioactivity. I'm just going to check where we are so that we know that we're on track. Okay, this is the last bit. You'd be glad to know we're nearly there. Okay, so when you look at an element, a bit of chemistry here, you're looking at the mass number, which is the number of protons and neutrons. You know this already from chemistry. We've had our chemistry exam, and that's the big number. The atomic number is the little number that tells you how many protons, which is the same as the number of electrons. So here, okay, you've got different mass numbers, but exactly the same atomic numbers. So we have isotopes. Okay, so with an isotope, again, overlap from chemistry, the same element, okay, they were all hydrogen previously, with different numbers of neutrons. They've got the same proton number, so that atomic number, the little one stayed the same, the top big one changed. When you have ionization, it's when you have radiation from a radioactive substance, and that knocks the electrons out of atoms. If you're knocking electrons out, the atoms become charged, and this could be harmful to living cells. So when an atom becomes unstable, it starts to decay. Okay, and when they're unstable, you can have too few or too many neutrons. And so when we have an unstable nucleus, I just imagine it like someone who's a bit crazy and about to have a hissy fit, is they will start to decay or emit, give out radiation, and giving out that radiation helps it become more stable. Okay, it's like when you're really, really cross or you want to shout at somebody, you're holding it all in, and then you get to a place where you can be by yourself and put your face in your pillow and just scream and let it all out. You become hopefully more stable. So when you measure radiation, you use a piece of equipment called a Geiger-Müller tube. And this measures a thing called the count rate. And it's like tick, 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 right? So the count rate is always much less than the activity of the source. And that's because the count rate is taken further away from the source, if that makes sense. So here, exam tip. Know the difference between count rate and activity rate, especially for 2 to 3 mark questions. So the count rate, okay, is measured in becquerel. Okay, and then activity rate, annoyingly, is also measured in becquerel. The activity is the rate at which a source of unstable nuclei decays, and this is decays per second. Okay, slightly confusing definitions on here, but know that you've got a count rate, okay, which is the activity that is captured by the Geiger-Müller tube, and the activity rate, that might help, is the rate at which a source of unstable nuclei decays, measured in decays per second. Right, I'm not going to talk anymore because I don't want to confuse you there. Right, so we've got 3 types of decay here that you need to know about, be familiar with, your alpha, beta, and your gamma decay. Okay, and again, had this been on a slide, it would show the things here, and I wonder if they're on the next slide here. No, that's really annoying. So with the alpha decay, I'm going to super quickly run through so you remember. When you have alpha decay going on, you've got a helium nucleus that's shooting out of the nucleus. Okay, and this means 2 neutrons and 2 protons are emitted. With beta decay, you also need to know that it doesn't penetrate very far in air. They are strongly ionizing. Alpha particles are stopped by a sheet of paper. They don't go very far, a few centimeters. Beta particles, again, I'm just referring to this one here. Beta particles are high-speed electrons. So we are emitting So they've got no mass and a charge of -1. They are moderately ionizing. They are absorbed by a sheet of aluminium, about 5 millimeters thick. Gamma rays is the last one, and these are waves of electromagnetic radiation released by the nucleus. They penetrate far into materials. You need, they're weakly ionizing. You need something like a thick sheet of metal or concrete in order to absorb them. Okay, so you need to know those. And again, hopefully you've got a book in your revision guide. I'm looking at page 44 in the separate science revision guide. You'll have more details in there. Okay. Right, health and safety precautions. Again, you've got your Geiger-Müller tube question. Right, I'm going to talk about this diagram, again, very conscious of time. So over time, you need to be aware of how different models of the atom evolved. So you had John Dalton in 1803 that came up with this atom as this indestructible particle and very simple. You then had J.J. Thomson. He then proposed the plum pudding model with electrons embedded in the sphere of positive particles. Ernest Rutherford, talked about this atom that has a dense positively charged nucleus here in the middle, and then electrons moving randomly in the space around it. Bohr's model in 1913 said the electrons move in spherical orbits around the nucleus. Awesome. And then we've got Schrodinger's model here in 1926, where he said there is electrons that are in motion, okay, in a cloud around a nucleus here. And then lastly, we've got James Chadwick down here, a British physicist that says there are neutrons that exist that have no charge, and atomic nuclei contain neutrons and positively charged protons, right? So this looks like it's the closest model to what we know of our current model. Again, experiments that were done. Okay, plum pudding model, these go into detail. Feel free to pause these and have a look at them as we go through. These alpha particles ricocheting off. This alpha scattering experiment, okay, with the plum pudding model. Okay, these alpha particles are passing through. And again, you've got a 3 marker here. Using the nuclear model of the atom, explain the 3 paths A, B, and C. So we're saying that A is going all the way through. That tells us that most of the atom is empty space. It doesn't deflect all the way through. Nucleus B comes to here, look. So you've got these, I'm assuming is electrons that they're firing, and these are deflecting off. This is showing that you've got a positive nucleus. You've got a repulsion of the alpha particles that's being shot at the gold foil. And then the nucleus in C, look, the nucleus is very small and got a concentrated mass. What's happening here is the alpha particles coming in. It is hitting the nucleus and bouncing off completely, right? So the central nucleus in the middle. So each of these lines represents 3 different things going on. Right, when electromagnetism interacts with atoms, electromagnetic radiation, you've got, they become excited, they absorb the energy or the photon in the electromagnetic wave, and it moves further away from the nucleus. It releases the same energy when it moves back towards the nucleus. Some of these slides don't make much sense. Okay, right. When you are doing these decay equations, you do need to make sure that both sides of the equation, the numbers are equal. So if you've got 241 at the top and 95 at the bottom, and this is decaying into these 2 particles here, you've got alpha decay, you need to make sure 237 and 4 add up to 241. Hopefully they do 37, 38, 39, 4, 44, 1. Yeah, they do. And then the bottom 93 and 2, they need to add up as well. Okay, big number, atomic mass, we already said mass number. Bottom number is the atomic number. Okay, this is the thing that's been decayed that we add on to here when you're doing these nuclear equations. Again, there's a couple of examples. Sorry, it's all gone a bit squiffy because it's supposed to be a PowerPoint slide. And then you've got another exam question here. And we're almost at the end, you'll be glad to know. So we've got half-life. This is the average time it takes for the number of nuclei of the isotope to halve. And so you've got the graph down the bottom, the number of half-lives, and up the side, you've got carbon-14 that remains. So at the beginning of the experiment, you've got 100% carbon-14. If you go down to 50% carbon-14, half of it's left because the other half's decayed. If you come across and come down, this is 1 half-life. They could give you a time down here. It could be seconds, could be minutes, could be hours. In this case, one half-life is 5,730 years. If we go from 50% down to 25%, that's another half-life. If we follow the graph along, okay, that's your 50%, one half-life, and then your 25% look, follow it across and come down, that's your second half-life. So there's another half-life between 50% and 25%, and that amount of time in real time is 5,750 years. Sorry, 5,730 years. Okay, so understand half-life. You may get a question like this again. Okay, it's all marked out on here. So you want to look carefully at the axes that you've got to calculate the half-life. Okay, this is another word problem here. Right, let's have a look. So we've got irradiation and contamination. When an object is exposed to ionizing radiation, it does not become radioactive, it is irradiated, language thing. Contamination is when a radioactive substance is present on a surface, substance, or within solids, liquids, or gases, including your body, where your presence is unintended. You don't want contamination. Okay, think about a biology experiment, sterile stuff. You don't want contamination. Background radiation is where you have a certain amount of radiation in the background, in the environment, that is always there. Natural sources such as rocks and cosmic rays from space. Okay, we've also got background radiation in terms of man-made sources, and this can be the fallout from nuclear weapons, testing, and nuclear incidents. This is a real worry. Okay. Now, depending on where you live, there's different doses of background radiation that you're exposed to. And you can have maps like this that show you the air quality related to radiation, or pollution levels, if you like. And these are measured in sieverts. You can use radiation for various useful uses. So we could look at thickness of paper when we're making paper here. Okay, and then with smoke alarms as well, they contain a source of alpha particles. And here, when you have smoke that comes along, it causes the alpha particles to be absorbed and stops the current flowing, and that makes the alarm sound. Right, this is where smoke alarms go off. You can use radiation to irradiate food to make it safe. So with gamma rays to kill bacteria. So if you're like, especially like if you're in a hospital or something like that, the food will be irradiated. Sterilizing equipment like surgical equipment, especially to kill microorganisms. We can use gamma rays to diagnose cancer. Okay, that's that. And then nuclear power here again, advantages and disadvantages. We did touch upon this earlier on. I'll just pop it up and then you can scroll through and have a look, see if there's anything that that you would just want to make notes on. And now we've got triple only, and this last section, as far as I remember now, should just be triple only on fission and fusion. Just passing you through. Nuclear reactors, right, we're done. We are there. Right, I'm just going to turn the recording off, and I wish you all the best of luck for your exam. Let's turn you